Good afternoon, good evening, good morning to those of us joining. For those of you joining us today for this USTTI FCC webinar, today we have David Dombrowski, who's the Regional Director for the FCC Enforcement Bureau's Region 1, who brings more than 30 years of hands-on field and leadership experience to today's webinar. With a background in electrical and telecommunications engineering and a career spanning roles as field agent, senior agent, and district director, he spent decades applying spectrum analysis in real-world enforcement environments. For today's session specifically, he'll introduce the fundamentals of spectrum analyzers, explaining key settings like resolution bandwidth, sweep rate, and show how these tools support accurate measurements, low-level signal detection, and direction finding. The general goal of today is David will give newcomers a clear, practical foundation that they can build on throughout their technical work.
Thank you, Jamal. Good morning, everyone. Good evening, those around the world. Thank you for joining the presentation today. We've offered this one several times now at USTTI. I get a little better each time presenting it. We've had technical glitches in the back, so if that happens, just bear with us. I am trying to demonstrate how to use a spectrum analyzer, so I have one physically connected to my computer, and I'll be sharing the display from the spectrum analyzer in addition to going through a slide deck. All right, so let's jump along. Again, yes, I'm the regional director. So I manage 4 offices here in the FCC Enforcement Bureau. They're all on the northeast area of the United States, and that is Chicago, that's Boston, that's New York, and then Columbia, Maryland, which is just north of Washington by half an hour, Washington, D.C. And I've been a field agent for many years, and the field spectrum analyzer is our tool of trade that we use pretty much every day for measurements and direction finding. So hopefully I'll be able to demonstrate some of these techniques to you. This course, again, is for really beginners, but those who are familiar with spectrum analyzers maybe can still gain some insights into how to use it a little bit better. We will cover what a spectrum analyzer is. We'll talk about the different types of spectrum analyzer, sweep and real-time spectrum analyzers. We'll look at the different settings because they're so important when doing measurements, getting those settings correct. Then we'll go through the different measurement techniques. Bandwidth, emission mask, and field strength are some of the ones we'll be doing. And then in the end, we'll talk about some recommendations when you're doing interference hunting. That is when you're looking for radio signals and you try to find where they're located, where they're originating, from what antenna. Sometimes those signals are very weak. We'll give you some tricks on how to locate them with the spectrum analyzer. All right, so what is a spectrum analyzer? It's a passive receiver, right? It's able to receive a radio signal and display that signal on the spectral display unit. And a radio signal is comprised, if anybody has had some engineering background, it's interesting. We've heard of sine waves and cosine waves. And we see one here in the red. That's a simple sine or cosine wave. A radio signal that's displayed on a spectrum analyzer is made up of many different types of sine waveforms that vary in amplitude and phase. And it's a combination of them. And what the spectrum analyzer is doing is processing that waveform so it can display it on the analyzer, and it can display the frequency versus amplitude, how strong that signal is and what frequency it's appearing on. It's useful for broadband detection. So if we have a band that we're operating in, say the cellular band, maybe it's 1.9 gigahertz, 1.94 gigahertz here in the United States, and there's multiple carriers or licensees operating in that band, we can look at the entire spectrum. We're not just looking at a small sliver. We can look at the entire spectrum and see how the signals are, what frequencies they're appearing on, how strong they are, and is there any overlap? Because when we start to get overlap of radio signals, that's what causes the interference. I have a designated channel, and if somebody is on my channel with their radio frequency emissions, it's going to cause me interference. And so that's a lot of the work that we do here in the field, is identifying where transistors are located because they're causing interference. They're overlapping someone else's spectrum. We want to make sure now in today's world that we have a high probability of intercept. In today's digital signals, a lot of them are on for very rapid or short duration in terms of microseconds. We want to have a high probability of intercepting them. The old spectrum analyzers, and I'll explain in a few minutes here why, but the older spectrum analyzers could not pick up some of the signals that are present today in the digital world because they're on so rapidly. The spectrum analyzer would just miss it and not receive it. So we want to make sure that the higher processing speeds of the spectrum analyzers today have a good chance, a high probability of intercepting that signal that is on for such a short duration. Now, there are different types. There's really 3 different types of spectrum analyzers. We have the older sweep analyzers. These analyzers use what we call the super heterodyne configuration, meaning that we have an oscillator that we tune, just like your car radio. When you're turning your knob on your car radio and tuning through the FM band, we're changing the oscillator frequency. And what we're doing is we're mixing the signals we receive through the antenna, and we mix it with the local oscillator, and we're able to force the band of interest on a particular frequency. And we pass that frequency through a filter, and then we can characterize that and show it on the display. That's what super heterodyning is. Again, we're passing the signals from the antenna into, or mixing it with a local oscillator. And if you know anything about engineering radio signals, if we combine frequencies and through a mixer, we generate, we can move that spectrum, say it's on 90 megahertz, we can move that down to a passband of maybe just 100 hertz, 100 kilohertz, and observe the spectrum there. So that's what the local oscillator does. We tune that band so we can move the spectrum around and process it through a filter, which doesn't change frequency. The characteristics of the filter stay the same, so we're passing the spectrum through that filter to display it on the analyzer.
And David, we have our first
Yes.
question.
Great.
For narrow banded signals and short duration signals like LEO satellite constellation, DL divided upon number of satellites, will spectrum analyzer be able to detect it?
Yes. So we connect spectrum analyzers to our satellite dishes, have a group that's right on the same property as where I'm located today in Columbia, Maryland. We have 6 satellite dishes, and they are connected to the spectrum analyzer. One of the things we'll talk about in a few more slides is the sensitivity of the analyzer. How low level of a signal can we receive? But also we can improve that by installing high gain antennas and with amplification, and we're able to pick those low level signals that are originating from satellites that are thousands of miles up in space. And we can differentiate them. If the beam width of the satellite is narrow enough, which they are, those satellite dishes that are 20, 30 feet in diameter, they have very narrow beam width. And so we can direct that antenna and point it right at the satellite of interest and pick out the signals just from that satellite. And we're not picking up the signals from the other satellites because of that narrow beam width. Hopefully that answers your question.
Great, thank you.
All right, fast Fourier transform analyzers. So I said earlier that radio signals are made up of sines and cosines of different amplitudes and phases. And there is some high-level mathematics that I had back when I was a undergraduate in engineering school, but I was talking about fast Fourier transforms of how we take signals in the time domain and present them in the frequency domain and convert them mathematically. And so we could do that through formulas and processing in the computers. And that's what newer spectrum analyzers are. They're fast Fourier transform analyzers because they have a computer that can take those analog signals and convert and digitize them and display them on the spectrum analyzer. And the processor speeds of the computers, because it has been so advanced over the last several decades, these are the analyzers that you see sold today, fast Fourier transform analyzers. We've moved away from sweep analyzers. This was just the super heterodyne mixing that I was talking about on a sweep analyzer, where we have a signal of interest in the green at the top here, and we're passing it through a mixer, and we can create images of that frequency. And the IF frequency is the signal that we pass through the stationary filter. we force the signal we're interested to pick up down to the IF frequency, which we have a filter design at, and that's what a sweep analyzer do. So it's a lot of tuning, and the processing time of a sweep analyzer is much slower than the fast Fourier transform analyzers today. And because of that processing time, in a true sweep analyzer, we lose a lot of information. So what we're doing is we're starting at the lower frequency of the band, and we're sweeping through the spectrum. We're changing that local oscillator, passing it through the filter, processing it and displaying it. And then once we reach our highest frequency of interest, we start the process over again. And we may miss a signal that is on for short duration because we may be in the lower spectrum and that frequencies is in the upper part of the band that we're looking at, and it's only on for a split second, and just in timing, we may miss it because of the processing speed of a sweep analyzer. But because of fast Fourier transforms, what they do now is they acquire spectrum in a certain limited bandwidth, and today's spectrum analyzers, the fast Fourier transform analyzers, they process an amount of spectrum, then they move to the next band, process it again, and then move to a higher spectrum, part of the spectrum that we're looking at on the display, and process that. Here, we still have lost information. If we're processing a spectrum at the lower end and a signal is present in the upper end, we may miss the signal again in a fast Fourier transform analyzer. But we now have analyzers that are called real-time fast Fourier transform analyzers, and they're band limited. The one I have on my desk today can only process 40 megahertz of spectrum at a time. So I can only look at 40 megahertz. I could process everything in that 40 megahertz span, and I have a very high probability of intercept. There are some better analyzers out there on the market that go up to about 110, 120 megahertz, a real-time spectrum analyzer, meaning that if you set your spectrum analyzer properly, you can observe the whole 5G signal. A lot of these 5G emissions occupy about 100 megahertz worth of spectrum. And so we can process that all at once and see the signal in real-time mode and not lose any signal as long as it's within that 120 megahertz of spectrum. Here you can see what a real-time spectrum analyzer versus a sweep analyzer. And we can show this on the analyzer a little bit later when we go and demonstrate it. If you look at the band, the center frequency is a 2.4 gigahertz band, which is the Wi-Fi band here in the United States and probably around the world. And on the left side, in our fast Fourier transfer sweep analyzer, we do not see any signals present. It's pretty much flat across the spectrum. But if I kept those same settings and moved to a real-time analysis mode, those signals of short duration, I can see them better. I have a higher probability of intercept, and now I can see them. That's the graph on the right-hand side. And so if the signal's on short duration, I have, again, a higher probability of intercept. Now let's look at some of the...
David,
Go ahead.
sorry. How can we measure satellite frequencies with the spectrum analyzer?
Okay, so satellites are typically operating in the gigahertz band. I have an analyzer that goes up to 14 gigahertz. Some of those satellite signals are up in the 50 gigahertz, 100 gigahertz spectrum. They have analyzers that go up that high, but they're very costly. The more bandwidth you want to observe on your analyzer and the higher frequencies you want to be able to receive, you could buy those spectrum analyzers. So they're more costly. You can also downconvert signals. You can buy a device called a downconverter, and it takes the spectrum that are on high frequencies and transposes it by that mixing, that super heterodyne mixing, and transposes it down to a frequency. If I'm band limited, my analyzer only goes up to 14 gigahertz. I could take the spectrum that's maybe at 100 megahertz, transpose it down to somewhere that my spectrum analyzer can receive, and I can observe it. And so you can also do it by frequency transposing, by buying devices that connect between your antenna and the analyzer. Does that answer the question?
If it doesn't, I encourage that person to send a second follow-up. But thank you, David.
Yes, please do. All right, let's look at some settings quickly on the analyzer, the basic settings. So here we have the spectrum analyzer showing on the bottom axis, which is typically the x-axis of our display. That's frequency. On the y-axis, which is the vertical axis, that shows the amplitude. And here we see two signals, one strong signal with a marker on it and one weaker signal. Span is how much spectrum we're looking at one time on our display. And in this analyzer, we have a start frequency of, well, it's too small for me to even read, but we can adjust that span. That's just how much spectrum we can observe on our analyzer at once on the display. The resolution bandwidth, and we'll explain this a little bit. We'll go into each of these settings. How about I do that now? Let's just introduce them. Resolution bandwidth, video bandwidth are settings that we can adjust on the analyzer. And we also have attenuators, which can reduce the amplitude of the signal coming in from the antenna. We'll talk about the frequency bins and the detector types and traces. All right, these are all settings that we're going to go through one by one. All right, we'll start with the resolution bandwidth filter. So in the super heterodyne analyzer, we're mixing signals. We're taking signal from the antenna, we're putting it through a mixer, and we're forcing that spectrum down to a known frequency that we can measure through our filters. And the most important filter in an analyzer is the resolution bandwidth filter. It means we're passing all the spectrum through this filter that we're going to display on our analyzer. And that filter can be very wide in bandwidth, or it could be very narrow. And the width of that filter, which we can adjust manually, affects our measurements. And let's see. Here we have a display of an analyzer. We have the blue, which shows a resolution bandwidth filter set higher, much higher than the resolution bandwidth filter setting for the signals that are displayed in purple. All right, these are three different settings for the resolution bandwidth filter: blue, yellow, and purple. And so as that filter is very wide, the resolution bandwidth filter, we have multiple signals passing through that filter at once. And so those signals combine to look on our analyzer as just one big signal, which is we show in the blue. And now as we reduce the bandwidth of that resolution bandwidth filter, we start to see the two signals, the distinct signals appearing. And that's shown in the yellow. We start to see, hey, there are two different signals here as we reduce the RBW. As we reduce the resolution bandwidth filter even more, we get to see the signal in purple and say, hey, there are two distinct signals here. So that is one thing that affects our measurements, is the bandwidth, how wide we set our resolution bandwidth filter. If we set it too wide, multiple signals are going to appear as one. And the sensitivity is another setting. How low of a signal can I observe on my spectrum analyzer? And that is determined by the resolution bandwidth, believe it or not. Here we have the average display noise level. Let's say that's the minus 120 dBm. That's pretty good for a spectrum analyzer, minus 120 dBm. And let's say there's a signal that's 2 dB above the noise floor. So that signal would be about a minus 118 signal if we measured the amplitude of that, because it's just 2 dB above our noise floor, and say our noise floor is a minus 120. And so display average noise floor is impacted by the resolution bandwidth filter. And here we show that in this graph. Here in the yellow, the top spectrum that we display on our analyzer, that resolution bandwidth filter is 1 megahertz. What's happening is that filter is so wide, we have a lot of noise, internal noise from the analyzer in that filter at once, and we have all the radio signals at once in that filter. And so our noise floor is going to be much higher because it's adding all that noise and all that energy from those radio signals together. And our average noise floor is a minus 75 dBm. That's very high. And we're not going to be able to look at very weak signals because our filter is so wide. So what do we do if we reduce the bandwidth of that resolution bandwidth filter? Look what happens. We start to see a decrease in the noise floor. It goes from a minus 75 down to a minus 85 in blue, down to a minus 95 in orange. And now we went from 1 megahertz down to 10 kilohertz. And we reduce that filter down to 1 kilohertz. Look what we get, a very narrow band signal appearing and a very low noise floor. All right, our dynamic noise floor is a minus 105 dBm. And so we improve our sensitivity by reducing the bandwidth of that filter. Let's go to our analyzer and just show this again because it's such an important factor. Okay, I'm looking at an AM signal here. And let's span out. Let's look at, let's see if we can get, let's go to the FM band. Frequency, let's go 99.9 megahertz, right in the FM band. And our span, let's set at, say, 10 megahertz. And look at all those signals we see, all right? There's a lot of signals here from the FM stations. And our filter set at 3 kilohertz. All right, but what happens? Look what happens when we increase that resolution bandwidth filter. We know that an FM station signal is about 150 kilohertz wide. And if we set it, let's say at 100, there's 100 kilohertz, we start to see that some of these emissions are disappearing and they're starting to combine into one signal. Look what happens when we go up to 300 kilohertz, right? Now we see less signals present, and they're much wider than we expect them to be. Here's 1 megahertz. Now we're getting all the energy of the noise and all the energy of those different stations in the filter at once, and it looks like we only have about 3 or 4 different signals present, which is really not the case here. So that's why we have to reduce that filter down, and I always suggest that we reduce it to about 10% of the bandwidth, occupied bandwidth of the emission. So it's a 150 kilohertz emission that we're trying to measure in an FM station signal. So let's go down to about 10 or 15 kilohertz. And that's about a good setting where we can distinctly see all those different FM station signals at once. Now let's go to a frequency band where there really is no signals. Let's go down to let's go to maybe 400 megahertz. And there's really no signal present here. This is just noise. And I'm going to increase, what's our noise for here right now? It's measuring at about a minus 110 dBm. And that's shown by the marker. Let's put that marker in the center. There we are, a minus 110 dBm. Let's change our resolution bandwidth filter. That's 10 kilohertz setting. Watch what happens when we drop it. We go down to 3 kilohertz. We see the whole noise floor lower. That's because less energy, noise energy, is present in the filter, and therefore the noise floor is presented differently and lower on the analyzer. Let's reduce it even more. Go down to 1 kilohertz. So if we're looking for weak signals, we can reduce the resolution bandwidth filter down maybe as low as we can go, but there is a limit. We see that as we reduce the bandwidth, right now we're at 300 hertz. That's really narrow. You can see that the processing time is a little bit slower. It's taken about a second and a half to go across the sweep time. Look at the sweep time. It's right down here in the bottom right corner. It's 1.2 seconds to sweep across that entire 10 megahertz of spectrum. So if you're looking for a signal and we know the frequency is, the signal is only occupying maybe 1 megahertz of spectrum, then why do we need to look at 10? Why don't we reduce that span to 1 megahertz? All right. So the less span and the narrower bandwidth of the resolution bandwidth filter, we can improve our noise floor and our sensitivity of our analyzer. Now we're down. We got another 10 dB. We're down to a minus 120 dBm. So you see how adjustments on the settings can impact your measurements, particularly looking for weak signals that causing interference. Adjust that resolution bandwidth to be narrow and adjust your span so it's more narrow, focused on the signal of interest, and we can get a really good sensitivity out of the analyzer.
And David, there's a question. What is the ratio of the setting for RBW to VBW?
All right, let's get into that. Go back to the slide deck, and we'll talk about the video bandwidth filter and how it impacts your measurements also. Let's talk about just in an fast Fourier transfer analyzer. It's doing sampling and processing. Like a computer needs to sample the signal and process it, and that slows down the analyzer in terms of processing time. So the resolution bandwidth filter has a little bit less impact on the processing time in a fast Fourier transfer analyzer. It's more dictated by the span, how much spectrum we're looking at one time. All right, the video bandwidth filter. So the question was appropriate, good timing. So the video bandwidth filter it's a low pass filter that comes after the envelope detector. I didn't want to get in too much about the electronics of an analyzer, but it determines the bandwidth of the video signal that will be digitized and displayed on the spectral display unit. When this filter bandwidth is reduced below the resolution bandwidth, the video system can no longer follow the rapid variations envelope of the signal. So you really don't want to have that filter, the video bandwidth filter, lower than your resolution bandwidth filter, because then, particularly these digital signals that vary rapidly, they're not going to be able to be processed properly, and it's not going to display appropriately on your analyzer. And what will happen is it will result in averaging or smoothing. So it won't be a real good representation of the signal that you're trying to observe. But sometimes we could use that to our benefit. Here in the video bandwidth filter, if we adjust it, on the left-hand spectral display, we have a video bandwidth filter of 30 kilohertz. And we see that there's rapid fluctuations in the noise. All right, the video bandwidth filter. So if we have a set of 30 kilohertz, we see there's large fluctuations in the noise. That's in the yellow, right? The spectrum here in the yellow across the span. But if we reduce that video bandwidth filter, what happens is we get smoothing or averaging. And so then it averages the noise, and which creates a flat line for our noise floor. And we're able to see the signal of interest a lot better in the noise. And so what looked to be only 5 or 10 dB above the noise floor, when the noise was on the left side, where the noise was varying rapidly, we can improve that signal to noise ratio by reducing the video bandwidth filter down to 100 kilohertz. All right, so the question here is about the settings. The degree of the reduction in the peak to peak variations in the noise is a function of the ratio of the video bandwidth and the resolution bandwidth. I typically just set the analyzer to automatic mode because there's a nice ratio between the two. I don't want to set the video bandwidth really below the resolution bandwidth setting. It's usually like a 10-to-1 ratio, where the resolution bandwidth will be 10 times smaller than the video bandwidth filter. But if we want to change the average display noise, we do manually want to adjust that video bandwidth filter and maybe sometimes reduce it below the resolution bandwidth filter. And that way we get that averaging of the noise, where it goes from what appears in the blue to the green, where it's nice and flat, and we can see weak signals in the noise, because it's tough to pick out signals when the noise is varying very rapidly. So hopefully that answers the question in terms of video bandwidth and resolution bandwidth. Know that there's a dynamic range in the analyzer. That is, if we had a strong signal that was peaked to the very top of the analyzer, it's a measurement of how weak of a signal that we can see in the noise floor. So that's pretty important. We want a very large dynamic range in the analyzer. So again, the signal on the right or the left side of our display, it's peaked all the way to the top level. And then we see on the right side the very weak signals that are down in the noise floor. Can we observe those weak signals, and how far down below the signal that's displayed on the analyzer can we see signals? And so in this case, it's about a 90 dB dynamic range on the analyzer. And that's where we're not going to see any spurious signals or distortion. And that dynamic range is impacted by 4 different things. What our average display noise level is, which we explained earlier, our 1 dB gain, compression points, spurious, and residual response. Let's go through them. Again, we talked about this. I don't want to hammer it too much more, but adjusting that resolution bandwidth filter improves our average display noise of the analyzer. Another thing is the 1 dB compression point. All right, the mixer and the amplifiers all are supposed to be linear, right? If you input a signal, you know what level you're going to get out, right? And so if it's a mixer, hope it's a 1-to-1 ratio. If it is an amplifier, maybe you get 10 dB of gain. So if you put a signal that's in there of 10 watt or say 1 watt, you're going to get amplification at 10 times that. All right. But what happens is if we start to overdrive the mixer, if we start to overdrive the amplifiers, we don't get that linear relationship anymore. And so we go into a realm where it's not a 1-to-1 ratio anymore. And we see on our graph that we're not really sure what the amplitude might be. It's not expected. And so if we expect an amplifier to give us 10 dB of gain, and we're starting now to operate in the compression point, we may only be getting 3 dB of gain. And that's because we're overdriving that amplifier. And so it's not a good representation. We don't want to overdrive our amplifiers. And so what I recommend to folks is that when we're inputting signals into our analyzer, try to keep the signals below a minus 30 dBm. That's always a good area to operate. You start to have signals coming in your antenna. Your analyzer usually tells you if you're being overdriven. It start beeping at you. But just to be safe, I like to keep my signals that are coming in from the antenna below a minus 30 dBm so I don't create distortion. And it's good if you're looking at a specific band, it's good to expand out because those adjacent bands that you may not see on the display are still coming into the analyzer being processed. And so it's good to span out the analyzer, look to see what's on either side of you. Are there really strong signals? There are. Let's reduce them with some attenuation so that we are not overdriving our amplifiers and going into beyond the 1 dB compression points.
And David, we have a flurry of questions coming in.
Okay.
And if you can see them on your screen, I'll still read them out loud. First question, is it recommended to use the function preamp on in interference measures at the uplink cell phone radio stations? There's any relations with uses of VBW?
Okay, so preamp. So all analyzers come with amplification, and we could turn that on and off. Usually the amplification is about 10 or 15 dB. And so signals that are in the noise floor, sometimes we want to turn that amplifier on, improve the sensitivity, so those signals will look higher on our display. You could also use external amplifiers that you connect between the antenna and the spectrum analyzer. But again, you don't want to overdrive the amplifier. If you're going to turn that amplifier on, it's good to span out beyond the span of interest and look to see what are signals that I'm not really measuring, but they're still near me on adjacent frequencies. Are they above a minus 30 dBm? If they are, I may overdrive my spectrum analyzer and get bad results. One way to overcome that, we'll talk about that later, is to use filters between the antenna and the spectrum analyzer so that we're not worried about those signals. We can attenuate those strong signals that are not appearing on our analyzer but can overdrive the amplifiers. We attenuate them, and that way they don't impact our measurement. And we'll talk about that in some slides coming up.
Okay, thank you. Next question came in around the same time. Where's the option for selecting automatic?
Automatic in terms of for the video bandwidth. I'm assuming we were talking about video bandwidth. So, okay, on my analyzer, I have a button called bandwidth, BW. So if I go to mode and bandwidth, here is the video bandwidth filtered set to auto. We could change it manually or just leave it at auto. So it automatically adjusts it with the changes in the resolution bandwidth filter. And that's how to adjust it on this analyzer. We go to the bandwidth and we just leave it in auto mode and let the analyzer automatically adjust the video bandwidth filter. Okay.
Okay, next question for intermodulation project generated by IMT systems that affect 2.5 gigahertz band. At what average line of sight distance can its disturbance be considered? And at what signal level, assuming the spectrum analyzer is properly configured in terms of resolution?
What signals are we looking at? 2.4 gigahertz band, and that was Wi-Fi routers, which are probably less than a watt. You just think those signals, if I'm walking away from my house with my iPhones are pretty sensitive. They can even pick up satellite signals nowadays and communicate through satellites. So I start to lose reception or connection to my Wi-Fi router when I get about 100, 200 feet away from the source, and that's inside the house. So now we have the attenuation of the walls. But if that router was put out in the open, it was nice and flat terrain, there was no obstruction, you're going to get a little bit further than that, maybe 100 feet or 200 feet, maybe 300 feet. But that's the expectation for routers. So you really have to be close to it. So if you're direction finding Wi-Fi routers that are inside a residence, you pretty much have to be in the street out front to pick it up with the analyzer. You can improve that again with gains, better antennas that are directional, and with amplifiers and filters, and improve the sensitivity of the analyzer. So we increase that signal. So you could put maybe a 20 dB or a 30 dB amplifier in line with the high gain antenna. Directional antennas gives you another 10 dB. And so we could probably greatly improve that reception. So those are some of the techniques to pick out the weaker signals, right? So then we'd go further away and pick that weak signal up if we use amplifiers, high gain antennas, and filters.
Great. And then lastly, shorter question. What's the level of noise acceptable in a video bandwidth?
The level of noise. Okay, so let's look at the adjustments here. So when I'm doing measurements, and I'll mention this again later, but if I'm doing measurements, let's look at, again, the FM band. And I'll go back to bandwidth. Okay, here we have our video bandwidth filter set very high, 5 megahertz, the highest level we can get it. All right, so we have it very wide. And right now, we're only looking at 1 megahertz of the FM band. So we see 3 stations here. We have the one, put a marker on it. We have one FM station signal here. And this actually is a digital sideband of that same station. And then we have an analog signal of FM station here, a digital sideband of station number 3. And there's the analog signal. Okay. And so 1 megahertz, we're looking at 3 different signals. And we're going back to video bandwidth filter. We set it at 5 megahertz. And then what is our resolution bandwidth filter? We usually set that around 1 kilohertz when we do measurements in the FM band. What happens if we set the bandwidth to the video bandwidth? We start to go below 1 kilohertz, below the resolution bandwidth filter. Watch what happens. We're going to start to get averaging and smoothing. There it's set at 30 hertz. It's below the resolution bandwidth of 1 kilohertz. And we're seeing that smoothing and averaging happen. And so we're not seeing all the frequency components. And so we like to keep it at 1 kilohertz or above. And you see you're not getting much change there, right? Once I keep it above the bandwidth of the resolution filter, we're not seeing much change in display at all. So RBW is 1 kilohertz. We're going to keep our video bandwidth at 1 kilohertz or higher. We start to go below that, we start to get the averaging, which is bad for measurements, but good for looking for weak signals. I hope that answers the question.
And I spoke too soon. 3 more questions.
Okay.
What is the maximum span range in measuring modulation for a FM frequency on an analyzer?
Okay, for measuring modulation. So we typically don't do a lot of modulation measurements, but we typically do our measurements with 150 kilohertz span, because that's when you're getting most of the energy of the signal in there. And so 150 kilohertz to 200 kilohertz would be appropriate for the analog signal.
Okay. Next question. Would it be difficult to read an uplink signal to a nearby site by adjusting the parameters?
Okay, so you're looking uplink signal from the mobiles from a handset, a cellular handset. Those signals are very difficult. Again, they're just milliwatts of power. You really have to be on top of them, within 50 feet of them, to see them. Again, using high gain antennas. That's what's so incredible when I think about receiving satellite signals that are so far in space, or base station antennas that are mounted on a tower. They're able to see those handsets very far away. And why is that? It's because they have high gain antennas that are designed just for that frequency band. So they're very high gain. They have great receivers that are designed just to receive that particular frequency band and no others. And so the sensitivity is very good in them, much better than a spectrum analyzer. And you have amplifiers. And so because of those parameters, a base station antenna is able to see the handsets much better than a spectrum analyzer would, because high gain antennas designed just for that frequency band, the amplifiers and also the receivers are designed just for that frequency band. The spectrum analyzer is a broadband receiver. So because it's operating broadband and wants to pick up multiple frequencies from 0 up to 14 gigahertz, it's not going to have as good sensitivity. And so I would have to be very close to that handset to pick it up.
And I mistakenly pushed a question away. The question was for narrow banded signals and short duration signals, like LEO satellite constellation DL, divided upon number of satellites, will the spectrum analyzer be able to detect it?
Yes, I do. I think the question was asked. I'm not sure if I'm answering it, because I think it's posed again. But even if they're narrowband, you can reduce your span on your analyzer. If it's a narrowband communication channel, it could be 10 kilohertz wide. And we should be able to differentiate those signals with the analyzer. As long as there's energy there, we correct our settings so that we're only observing a small portion of the spectrum, and we have good sensitivity, we should be able to differentiate those narrowband signals, even coming from low Earth orbit satellites that are still hundreds of miles up in the sky. As long as it's there and we have our settings set properly, we should be able to observe them on the analyzer.
Okay, thank you, David.
Remember, the analyzer, the bandwidth filter goes down to hertz. So if the signal is only several tens of hertz wide, we still be able to differentiate that. We just have to really span in on that signal and reduce our resolution bandwidth filter so we can observe that very narrow signal. That's why these settings are so important. So spurious responses, again, because there's mixers and amplifiers, we can get distortion, those signals mixing in the analyzer. And if we have two frequencies, F1 and F2, which is shown in the blue, we create multiple products of those. And you can see the mathematical formulas where we get first, second, and third order intermodulation. And so that happened in our analyzer. And so it may present a signal that we see on our display, but it's not really there because it's created in the analyzer. We've seen this happen. We go up to tower sites. Those signals are very strong because we're right at the tower site. And what's happened is you overdrive your receiver, you overdrive your spectrum analyzer, and we start to see intermodulation products. The entire noise floor goes up. We start to see frequencies present that really are not there. And you may drive yourself crazy trying to track those signals, and really they're generated in your analyzer. So that's what we have. You could do a test in the analyzer by adding attenuation. And if you start to add 5 or 10 dB of attenuation, and those signals do not reduce the same amount in your analyzer, then you know it's intermodulation generated inside your analyzer. That's always a good test to do. So again, if I have a signal present and we think it's intermodulation, we can add attenuation in the analyzer, 5 or 10 dB. That signal that's present on the analyzer should drop 5 or 10 dB. All right, so that's important, and that's a good test to do. Residual responses, this is just signals created by the analyzer internally. They're not in modulation. They're actually just signals created by the circuitry of maybe the oscillator or some other electronics, the computer electronics, and they generate radio frequency emissions, and sometimes they'll appear in the band. Now, we want to buy an analyzer that doesn't have these residual responses. So if you buy a cheaper analyzer, this is what's going to happen. You're going to see a lot of spurious intermodulation products, and you're going to see a lot of residual emissions where signals, again, they're not present over the air. They're actually just internally generated. So the higher end ones that cost tens of thousands of US dollars are going to have less of these emissions. So here's the analyzer test I was just talking about, inputting attenuation. Now I want to show that you can have an external attenuator between your antenna and the analyzer. And if you put 10 dB of attenuation, the emissions that you measure on your analyzer will go down 10 dB. We also have an internal attenuator in the spectrum analyzer. And what happens is, and just be aware of this, I'm going to go back to my spectrum analyzer. If I go to mode and amplitude, I see over here RF attenuator. It's set to auto, but I can move that to manual. And right now my attenuation is 0 dB. Let's put a marker actually on this center frequency here. And look, let's measure that. It's coming in about a minus 78 dBm. Let's just say it's minus 80. If I go back to my attenuator and I increase that 10 dB, notice that the signal is still measuring about a minus 80. I didn't see any change. What's happening is the analyzer is compensating. I know we're getting very frustrated with this flipping of the screens. The analyzer is compensating for the attenuation that I'm putting in. So we're not going to see changes in the output levels or the amplitude levels of the signal, even though we are adding attenuation in. So just be aware of that. We add 20 dB, the signal is not going down to a minus 100 dBm. It's still at a minus 80 dBm. But what is happening is our noise floor is changing. And I could show that by going back up to, say, 400 megahertz where there is no signals. Here we have 20 dB of attenuation. Here's a 20 dB of attenuation. Look at my marker. Let's see what's measuring here. Our noise floor is a minus 100. If I change that RF attenuation down to 10, all it's doing is actually changing just the overall noise floor. It's not changing the amplitude of the emissions that we measure. It's changing just the noise floor. So just be aware that we manually add RF attenuation into our analyzer.
As you transition here, a question came in. As the uplink signal is unstable a little bit in cellular network, what is the best way, based on your experience, to detect it, analyze it, and find out solution for interface by using a spectrum analyzer, in particular when the traffic is very low?
So unstable, I would think in terms of unstable, maybe frequency instability or amplitude instability. Maybe they can specify, or maybe we're looking at both parameters. We don't do a lot of tracking of handsets here. The FCC doesn't. We rely on the cellular providers to resolve their own interference issues among their handsets. But if I was looking that if we're trying to track it, what's the best way to analyze it? We want to measure the frequency of the handset. And so you're going to have to know what band it's supposed to be appearing on. And you can measure the frequency in an analyzer by looking. And how about the emission bandwidth, the emission mask? I think we'll answer this when we talk about emission masks. Emission masks are limits set up for how much bandwidth a signal can occupy. And so let's hold on to this question when we get to emission mask measurements. That's going to be very important. Just to know that there are different types of detections. I don't get into this too much. An analyzer does have different detector modes. There's sample, maximum, negative, normal, and average. And so let's just introduce them to you. I always put the analyzer in auto mode so it automatically detects it, and it usually puts it in peak. Maximum peak detection is usually what the analyzer automatically defaults to. But sample detection, what's happening is your analyzer is sampling the spectrum. Right? It takes multiple samples on a particular frequency. All right. And that's called a bucket, right? One specific frequency. It samples it multiple times. And you can see when it's sampling it, the amplitude can vary. And we can represent that one point on the analyzer, right? Our display is made up of 600 to 1,000 different points. And so that one point can be represented by the peak level of the signal that we sampled on that one particular frequency. It could be the sample. If we use sample detection, it could be right in the middle level of our samples. So we talked about positive. So you can see that negative peak is the lowest level of the samples that were taken to represent that one data point. And normal detection, this is very complicated, but we look as we take multiple samples to display one point for a particular frequency. If we have two peaks, displays the maximum minimums of the sample data. And it does an algorithm here. I'm not going to go into detail because it's not that important. But you can look at the slide deck or look that up. But normal detection does some sampling, and it looks at the positive peaks and the negative peaks, and it tries to represent that data differently. And there's average detection. What is the average of those samples taken? And so I just want to introduce that to you. You may see that on your analyzer, that there's different settings, detection settings. And you could, I'm trying to think, I made a note where you could find that. It is under the trace. Yes, it's under the trace menu on a field Fox mode, and hit number 6. You go on a trace and you can change the detector settings. And in mine, I set it to auto, which always defaults to peak detection, which is best for locating carrier wave signals. Sample detection is best when you're doing noise measurements. And so there's different detector modes on there. I wanted to introduce that. I'm not an expert on it, but I just wanted to say, hey, they're present there. Trace, probably easier to demonstrate this on the analyzer itself. And it's the last one before we get into the measurements. Okay, if I go to mode on my analyzer and number 6, that's trace. And you can see, let's go to the 99.9 megahertz band, which was the FM band. There's our signals present again. And right now we're looking at instantaneous. It's measuring the spectrum and representing that data, and then it measures it again and displays it, the data. So we could actually put a second trace on here, and we could set it at max hold. And that's shown in the red. So what happens is it collects all the data for each frequency point and says, okay, is this signal the highest level measured yet? And if it is, I'll display that in the red level, the red trace. And so we could look for the maximum levels versus the instantaneous levels. We could also set a third trace and look at the average. What's the average of that? And that's shown in the blue. And you see the average is not going to change much, right? After we take multiple samples, that average is not going to fluctuate, even though the instantaneous is fluctuating greatly, shown in yellow. And the red's not going to fluctuate much after we take multiple samples because it's the maximum. It usually goes to a certain level and doesn't exceed that after we collect a significant number of samples. So those are usually the basic traces that we set: maximum, instantaneous, and average.
Dave, before we make this change in sections, we have 4 questions. First question being, in the case of aeronautical interference, can the system managing ground to air equipment cause its own interference?
Do we have an aeronautical system? It's trying to monitor the aircraft in the band. They typically in the United States operate, and probably all over the world, 108 megahertz up to 132 megahertz, I think, is the aeronautical band typically for pilots to communicate to the tower. Okay, so yes, you can create your own interference. There was a presentation earlier the week on interference, and I'm sure Shannon Gunter covered this, but we talked about intermodulation. When we put multiple antennas, high-powered antennas next to each other, you can have intermodulation. And so those signals would happen if I have an antenna and I have another transmitter nearby, that signal from that other transmitter can come down to my antenna into my receiver. Because it's so strong, it overdrives my receiver and now creates intermodulation. And so that will increase my noise floor, decrease my sensitivity, just like we explained in the spectrum analyzer. Those same things can happen in radio receivers. Because a spectrum analyzer is somewhat of a radio receiver, a little bit different. But some of the problems that get generated, intermodulation, that's typically what we'll see when we create our own interference is intermodulation at a site. And so the best way to eliminate that is to put a filter, a bandpass filter, so then I'm passing just my frequency that I'm transmitting on, and I'm reducing the emissions from other transmitters coming down into my antenna. You can significantly reduce them. Those filters can knock the signal down maybe a minus 50 dBm. And so, yes, you can cause your own interference that way by intermodulation. Maybe something inside the room, the building is causing interference. Maybe a computer can put out emissions that it's very close to the antenna. So you should sweep the building first and then tap into the antenna to look for the interference source. And if you tap in the antenna, you're not seeing anything, then maybe it is intermodulation internally generated. Hopefully that answers the question. I'll go too deep into that because it is another presentation.
Okay. Next question. Actually, I'll give you 2 questions. It's from the same person. Under what conditions would narrowing the radio bandwidth worsen the accuracy of peak detection? And how could measuring results differ if signals has rapid amplitude changes within a bucket?
Okay, so a resolution band filter, we set it 1 kilohertz. I like to set it at 1/10 of the occupied bandwidth of the signal. The occupied bandwidth again here is 150 kilohertz, so we go down to about 15 kilohertz, 10, maybe 1. If I start to go below that, all right, look at what happens in the amplitudes. I'm down at 300 hertz, and you saw that the maximum levels dropped, right? Here, when I go up, if we start to go too low, see our maximum levels are dropping a little bit. And so if we reduce the bandwidth too much, it's not going to display the amplitude appropriately, and we're going to get inappropriate measurements. It's not going to be a real representation of what the amplitude is. It's going to be actually show it lower than it actually is. I didn't think I mentioned that earlier, but you can set your resolution bandwidth filter too low. So a good 10-to-1 ratio is appropriate. 1/10 of the occupied bandwidth of the emission we're measuring. All right, now we're going to get into measurements. I always use broadcast to help make my points here, but I'm going to go down to 1.01 mode. Frequency, 1.01 megahertz. I'm going to span into, this is a AM signal, amplitude modulated signal down at 1.01 megahertz. And we know in amplitude modulation, the carrier doesn't change in signal level. And so our first measurement is just to measure the carrier. The spectrum analyst could be used as a frequency counter. And so how I do that is I zoom in on the signal of interest. I'm only looking at a span of 20 kilohertz. These signals really only occupy 10. We can even go down to a span of 10 kilohertz. And so there's some modulation on that signal. Maybe I change my amplitude a little bit. So there is our signal. And if I go to trace, And I want to put a marker. Let's on the maximum. And so I'm going to measure, I go to mode and I go to marker. And now right here in the far right corner of the blue menu is called frequency counter. I could turn that on. I probably want to put marker right on the center, 1.01 megahertz. And right now, our marker counter, MC1, is 1.01000002 hertz. All right, so that's an accurate frequency measurement. Easy to do when the carrier is not fluctuating greatly. So if you have one that's an FM station signal, you may want to put it in max hold and then do the measurement and measure the carrier that way. But here in a live signal, amplitude modulated, the carrier doesn't fluctuate. And so we could use this analyzer to accurately measure the frequency of the carrier. All right, so that's measurement number one. So that's what I was just saying there. Frequency counter, measure the signal. Occupy bandwidth. There's two different types of bandwidth measurements we could do. We could do the 99% power. That is where all the 99% of the power across the signal is contained within the upper and the lower frequencies. It's the total mean power. And so the only way to do that is to have the analyzer measure this. And we can demonstrate that. Let's look at an LTE signal. Let's first describe the measurement, and then we'll go, so we're not switching back and forth. Let's describe the bandwidth measurements, and then we'll demonstrate them. Occupy bandwidth, 99% power measurement, where 99% of the power is between frequency 1 and frequency 2. And the analyzer is for an LTE signal, and typically the LTE signal, a 10 megahertz LTE signal, will occupy 9 megahertz of spectrum. That was a measurement done here. There is also, and here's what a fast Fourier transform, you can set it up to do that measurement. And the only way to measure this is with a computer, a spectrum analyzer. There is another measurement. These are XDB bandwidths. And what you do is you look at the peak signal, and then you look to see where the emissions are attenuated, at least in this case, 26 dB below the carrier. This is a 26 dB bandwidth measurement. And so we can do a max hold on the signal, and we could put markers on our traces and show frequency 1 and frequency 2 where it's attenuated 26 dB below the peak level. And that would be the bandwidth doing the XDB bandwidth measurement. And that could be done manually with markers and traces in the analyzer. And so here are some measurements done with the analyzer. Usually we do a 0 dB reference. What we do is we do a max hold on the signal, and we move the spectrum all the way so that the highest frequency touches the top of the analyzer. That's what we call 0 dB referencing. And that's a lot bit easier to measure. So we know the top line is our zero reference, and then we can measure 26 dB down and look to see where those frequencies appear, where all the emissions beyond that are 26 dB or more attenuated. So let's do that demonstration of these two bandwidth measurements. Okay. I'll go back to my spectrum analyzer. I'm going to go to frequency measurements is 1.97 gigahertz. Let's take some of these traces off. Mode and trace. Blank that one. So we only have one trace here. Okay. And we don't see really any signal there, right? But look at our span. Our span is only 10 kilohertz. Let's go out to 10. All right. So here is an emission that we want to measure the bandwidth on. And we could do it two ways. I'm just going to put a little amplification. I normally don't do this, but we're a little bit further distant from the station. So I can go mode and measure and channel measurements. And occupied bandwidth is what I'm interested in. And see, this automatically sets it up. There's two limits here. There's the lower limit and the upper limit by these yellow vertical lines. And they're saying that all the 99% of the station's emissions, power of these emissions, is within these two frequency points. And it's measuring the occupied bandwidth is 9 megahertz, even though it's a 10 megahertz wide channel. So that's one way to measure it. It's just a couple pushes of a button, as long as you set it up so that your span is set up so you see the entire spectrum of the signal, and you have pretty good signal to interference, signal to noise ratio, 20, 30 dB above the noise floor. You can accurately measure this. We're going to turn this one off. The second method is to use markers. Now, if I set the marker here, and let's say I'm measuring, say, the 3 dB point, all right? That's about 3 dB below the peak level of the signal of that marker on the left side. And then I go marker delta, and I go all the way over to the other side, and I measure where it's 3 dB down below the peak level. And you see my bandwidth is almost the same, 9.075, almost 9.1 that we measured using the 99% power measurement. We're a little bit off because we're not measuring exactly 3 dB down. It may just be off with a hair, but relatively the measurement is the same as the occupied bandwidth. So we're looking at, we're in this case, 3 dB below the peak level. There's two different bandwidth measurements right there. 99% power and the XDB bandwidth measurement.
As you're transitioning, there was a question. Can you explain the difference between P-scan and scan? When should P-scan or scan be used?
You're talking on the Radio Source PR200. There's P-scan and scan. I'm familiar with the terms, and that's a receiver. The PR200 is not a spectrum analyzer. Radio Source will say that. And I'm sorry, I cannot answer that. I just don't use the PR200 often enough to know the difference between the two, the P-scan and the scan. But if you copy my email address down, I could get you an answer. We have guys here that use the PR200 quite often, and I can get you an answer for that, okay?
Great, thank you. And then what is the importance of SWP, time to determine RBW?
All right, so we're talking sweep. What is the importance of sweep?
Time to determine radio bandwidth.
To determine the resolution bandwidth. Okay, so when we, in a fast Fourier transform, the sweep was impacted, or the processing time was impacted by the span, how much frequencies we're looking at and processing at once, not so much on the resolution bandwidth filter. In the old sweep analyzers, again, if we have the more narrow, I'm not going to demonstrate this again, the more narrow we set the filter, the faster processing time. Let's just look at this signal frequency, 99.9 megahertz. Right now, this is a frequency span of 14 gigahertz. And what's our resolution? And we see that's pretty instantaneous. We're getting the changes pretty rapidly. That's probably because our filter is set pretty high. It's set at 5 megahertz. What happens is we decrease it down to 1 megahertz. See now that the updates are much slower. All right, so it does impact the resolution bandwidth filter, does impact the sweep rate of this analyzer. And we go too low, it just becomes painstakingly too slow. It takes us, again, 5 seconds to go across the entire spectrum. And that's shown right here by the rate in the corner. It says sweep is 5.8 seconds. Our resolution bandwidth sets too small. It's too narrow. We have to go a little bit higher, 5 megahertz, and that gets us almost instantaneous. It takes us 150 milliseconds to go across to process the entire spectrum of 14 gigahertz. Yes, there is a relationship between the two. All right. All right, we're at 11:30. I want to run through a couple things on the presentation slides. Okay, spectrum analyzer measurements. One of the ones we use the spectrum analyzer a lot for field strength measurements. We want to measure the electric field strength in volts per meter. This is a measurement highly used to determine the strength of a radio emission, particularly for EMC compatibility, electromagnetic compatibility measurements, where we do them in a lab in the anechoic chamber. You're measuring the field strength. So you need an antenna set. And this antenna set is typically a dipole kit. We could buy these dipole kits. We have a dipole kit that goes up to 1 megahertz, because a lot of our measurements are up to 1 gigahertz. Most of our measurements are done below that band. If we have to go above that band, we'll have to buy a very specific dipole antenna that's for just a specific frequency band. So you could buy a dipole kit depending on the frequency. So here, dipole kit that we have is Pro, I think it is. And you can see there's different balance. There's different balance there for each frequency band. So the shorter the balun and the shorter the element length is a higher frequency. So again, this kit does up to 1,000 megahertz. But what you need is the antenna factor. You need the manufacturer to determine what the antenna factor is. And that's so you can convert a signal strength in dBm to a electric field strength of dB volts per meter. All right, so you need to know that antenna factor. And to do a measurement, what we first do is we could change the settings. We could just change the display settings. So instead of reading in dBm, which is a signal level measurement, a voltage across the antenna port, we're going to change that to dB microvolts. And then we can go into the channel power measurement mode and integrate over a specific bandwidth. And so here is an example of the display. And what this frequency is 106 megahertz. And we're measuring just the analog portion of the signal. You see there's a digital sidebands here. Those rectangular shaped emissions are the digital emissions, but we're measuring the analog portion between this point and this point. We're integrating across 150 kilohertz and measuring the power across that. And so we have to change the setting so it's reading in dB microvolts, measures that as 51.76 dB microvolts across 150 kilohertz. And then we use that antenna factor to convert it to dB microvolts per meter. All right, so that's where you need to talk with the manufacturer about buying a dipole kit that has a set of antenna factors. And if you look back, the antenna factors, there's only let's say there's probably 30 different antenna factors here. If you're measuring, say, between 30 and 35, maybe you're measuring 34 megahertz. And you see, we don't have an antenna factor for 34 megahertz, where you're going to have to extrapolate out. All right, you're going to have to use some mathematics to determine what the antenna factor is. Just assume it's linear between the antenna factor for 30 megahertz and between 35 megahertz. And it should be somewhere close to minus 0.5, but a little bit lower. All right, because we're measuring 34. So let's go. Let's look between 160 and 180. You see the antenna factor is 12.7 and 13.7. If we wanted to know what the antenna factor is at 170, we just assume that it's linear and that it's right the midpoint between, and that would be 12.7 plus a half a dB. So that's 13.2. That's right here. It's 160 to 180. It's 12.7 to 13.7. Assuming it's linear, if we wanted to measure at 170, our antenna factor will be 13.2. So that's how you can determine the antenna factors for a specific frequency and measure the field strength. All right, now we go back to the emission masks, and this came up in the question of measuring the handsets. Every signal that we allocate is authorized a certain bandwidth to operate in. It's an occupied bandwidth. Anything outside that band is unwanted emissions. These should be greatly attenuated so they don't cause adjacent channel interference. Anything that's well beyond a megahertz or beyond the center frequency is called spurious emissions. The emissions that are close are out-of-band emissions. They can cause adjacent channel interference, but they could also be very far away from, several megahertz away from the center frequency. And that transmitter generates spurious emissions, and they can also cause interference. All right, so we want to make sure those emissions are all attenuated greatly. You're talking minus 50, minus 80 dBm below the center frequency. And so for every frequency band, we've developed what we call emission masks. And here is one for the AM band. You can see that the carrier in the center is given unrestricted. There's no attenuation, right? We don't need anything around the center frequency. But as we get further and further away, that the attenuation requirements increase. And so as we get, 80, probably 80 kilohertz from the center, it's greatly reduced. It must be attenuated 80 dB down. And that's to avoid, again, adjacent channel interference. And so we had this, I'll just fast forward, we had this for the FM band. We also have it for land mobile two-way radio. There's different emission masks, A, B, C, and D. We could talk more about that offline if you want to. And so here's one for a digital emission mask for a digital land mobile radio, two-way radio. And that this signal meets that. We measured it, and it's all within that red line of the emission mask. Nothing exceeds. It's very close, but it doesn't exceed it. And one thing I want to measure is, how do we do these measurements? First of all, let's say for an AM station, our rules require that you go 1 kilometer away from the source. You want to go a little bit away from the source so that you're getting sufficient signal level from the transmitter, but you're also not getting interference from adjacent channel and co-channel users. And so 1 kilometer is good for a broadcast station. We also do that for FM, 1 kilometer. They should be conducted about 1 kilometer away. For a handheld radio, you're going to measure in the same room, maybe 3 meters away. And what you do is you turn the transmitter on and you set your analyzer to max hold. All right. Set it in max hold, and you measure the emissions over a good length of time, a minute or two, so that you can gather all the peak levels of the emissions. And then you see do the emissions exceed any of the emission mask. And in this case, this FM transmitter does not. Its digital sidebands on either side of the analog signal come very close to that red line. It's only a few dB below, but it doesn't exceed. And so when you're measuring handsets, let's just assume this is a signal from an old LTE handset. You would measure the emissions. You would measure it in frequency, make sure it's right on frequency. You would measure its bandwidth to make sure it's occupying the right amount of bandwidth and not creating out of band or spurious emissions that cause interference to adjacent signals. And so these are the measurements that you would do if you had a handset that wasn't working properly. You could document this and say, hey, look, this handset doesn't meet the emission limits, and therefore it needs to be turned off and replaced. There's something wrong with the electronics. And if you attended the interference presentation earlier this week, Shannon was talking a lot about interference, co-channel, and adjacent channel. And spurious emissions are very important. We have to attenuate those because those are the ones that we always find. The transmitter may be operating properly and still communicating properly, but now it's generating some of those spurious emissions outside the band and unknowingly causing interference to adjacent channel users. All right, spectrum analyzer options. Just know when you buy an analyzer, there's a lot of different options you can buy. Here on our analyzer, we have remote control capability. We have a tracking generator, meaning we could generate a signal on any frequency. We have the preamplifier. We have the spectrogram, which I did not show yet. We also have time gating. We have the real-time spectrum analyzer mode. We can demodulate the signals. And there's a lot of ones that we don't have in terms of measuring like LTE and 5G signals. We don't have that capability in our analyzers. We have some other specialized equipment that does that. So you have to buy each separately these options. They cost money. Let's go through just in about 5 minutes and we'll wrap it up. Interference hunting recommendations. I mentioned this already. When you're measuring signals, always put a filter between your antenna and the analyzer. That's actually a narrowband meter for RF exposure measurements, but it also has a spectrum analyzer inside of it. Here we put a filter on it just so we can attenuate signals that we're not interested to measure so they don't impact our measurements. Filters have a specific bandwidth. You could buy filters that are very small and light, and they're very frequency specific. And so you go to a manufacturer, say, hey, I want a filter that has 50 megahertz of bandwidth. It attenuates anything outside that bandwidth by 50 dB or greater. Or you can have one that's a very narrow bandwidth, such as one for like land mobile radio, where the channel is only 12.5 kilohertz wide or 6.25, and you want a very narrow filter so you don't cause adjacent channel interference or receive adjacent channel interference. There's also tunable filters, and you see the one at the top here in this picture. This one does a specific band, but you can actually tune it, and it's a few megahertz wide, depending on what you buy and what the specifications are, but they aren't very narrow band. And so this is good if they're bulky, but they're cheap and relatively cheap because you don't have to buy these individual narrowband filters. You could buy a wideband tunable bandpass filter and get pretty good attenuation. So if you're monitoring here in the United States, the lower 800 megahertz band and looking for the signals from the mobile handsets, you can attenuate the emissions from the base station that could cause interference that are about 45 megahertz away. A tunable bandpass filter does very well for that. We showed earlier the traces where we did a max hold versus instantaneous. And so this is how you direction find. You set up the trace so that it records the maximum level, which is shown in the blue. And then in the black, the signal level is the instantaneous. And if you put a directional antenna on your analyzer, you can rotate, just turn your body or the antenna 360 degrees and look to see when the black emissions, the instantaneous emissions, reach the peak level. So what you do is you start at one point and you slowly turn around 360 degrees and capture the max hold and do one rotation. And then you start very slowly rotating again, looking for what direction is the maximum signal. Now that's a lot of times it's dependent on the antenna. If you have a very broadband antenna, the beam width is going to be very broad, very wide. All right. So pay attention to the beam width of your antenna. Sometimes they're 30 degrees beam width. And so you're not going to get very good accuracy. To the narrower beam width you have on an antenna, the better direction you're going to get of the signal. So pay attention to that, to the beam width of the antenna, and rotating that antenna around and finding out where the maximum is. Also, if you have a poor antenna that doesn't have good front to back ratio, meaning that if I point the antenna toward the transmitter and get a signal level, and then I rotate my body 180 degrees, you're going to get some significant emissions off the back of the antenna, but they should be at least 10 dB attenuated below what you would get off the front of the antenna. So pay attention to not only the beam width of the antenna, but the front to back ratio of the antenna, so that it's at least 10 dB attenuation, or 10 dB attenuation. Otherwise, you're not going to get good directionality out of it when you're direction finding. Persistence. I want to demonstrate this. I'll be the last thing I do. I'll come back to this. Time gating. Just be aware that a lot of the cellular companies now are using spectral efficient transmitters where uplink is in the same frequency band as the downlink. And I'm going to copy this YouTube link in the chat before we go. And so we'll give a second before you drop off if you want this. But this video I have here, I'm not going to play it, but it shows you how to set up the analyzer so that you can attenuate this emissions from the base station while you're monitoring the transmissions from the handsets, if they're operating in the same frequency band, which some of them do in this time division duplexing. It's a little complicated to demonstrate here, but the video is about 10 minutes long. I'll give you the link, and it was done by a cellular provider. So just be aware of that, but you have to buy the option of time gating for your analyzer. And so what it's doing is sampling only when the handset's transmitting, and it's not sampling the spectrum when the base station's transmitting, because each one gets its own time slot. Spectrogram, just be aware that there is a spectrogram where this is helpful. A lot of spectrum analyzers have this, and you could change these settings, the color settings. What you see here in the noise, I'm looking at the spectrum here display, and I see a lot of noise. I can't really see signals in there, but look at the spectrogram. If you run the spectrogram, what this is showing is signal level over time versus frequency. So the bottom part of our graph is frequency. Instead, our vertical axis is time, not amplitude, but time. And so we see that at one point in time, there are some constant signals here. There's about 4 constant signals, maybe 2 in between these two. So there might be 6 constant signals here present that we don't see in the noise. So the spectrogram is very useful. I'm going to show that before we drop off persistence and spectrogram real quick. And another thing we can do is changing the scale. And this is the last slide here, and I'll go back and demonstrate 2 things on the analyzer. But if you're looking for weak signals, typically an analyzer on the vertical axis will show 10 dB per division. All right, so it goes from 46 dB to minus 56 dB to minus 66. Well, what happens if you're looking for a weak signal? You could change those settings so that it's every 3 dB per division. So now you can go from the signal was down at a minus 105 dBm. We'll change it so that the vertical axis is 3 dB per division, and you can actually pull that weak signal out of the noise a little bit better. So just be aware of that. Changing the y-axis, the amplitude axis, so it's 3 dB per division really helps pull the signals out of the noise. All right, so let's show 2 quick things, and then we'll wrap it up for some final questions. All right, I'm going to go and show the spectrogram. All right, we're going back to frequency 1.97 gigahertz with a span of 10 megahertz. It will go even higher. Let's go 20 megahertz. And we're going to change our original band filter so we can see signal in the noise. There we are. Okay. One interesting thing we can do is in the real-time mode, and I changed all my settings, didn't it? 1.975 gigahertz. All right, and the span, we're looking at 40 megahertz. This is the entire bandwidth of the real-time analyzer. So we see a couple of different LTE signals here that are rapidly fluctuating. This is called the persistence mode or real-time mode. And it's interesting. It helps in this mode. It helps us in the real-time mode. We have a high probability of intercept, and also in the changing the persistence, which I go to here under sweep. This is the hold time of these signals. What it does is it samples it and it holds it just for a few milliseconds or even up to 5 seconds. It kind of holds that signal so that you can see the rapid fluctuations. Probably a little bit easier to see in the, I'm going to go to I'm going off the antenna and using one right here in the office. And if I go to the 2.45 gigahertz band. All right. This is the Wi-Fi band. Bluetooth, Wi-Fi signals here just in the office. Probably my Wi-Fi routers are working in here. My cell phones are on the Bluetooth connection. And we see these signals. With persistence, in the real-time mode, I can change how those signals appear on the display. Right now, the persistence is set at 850 milliseconds. If I increase that to, say, 1 second, what it does is it actually holds the signal. You can see how the frequency hopping is occurring. It's a little bit clearer to see the frequency hopping. So this is done in real-time mode, changing the persistence, how long the signal will display on the analyzer. It holds it, and then it dissipates. So it helps brings out those signals that are frequency hopping a lot easier. So if you're direction finding Wi-Fi signals, LTE signals, 5G signals, use the real-time mode and change your persistence to hold that signal a little bit longer. And then the last thing I was going to do is show you the spectrogram. I don't know how well the computer is keeping up with the spectrogram here, but what the spectrogram does, again, on the x-axis is frequency, on the y-axis is time, and then it's color-coded by how strong the signal is. So you see in the red, we see some red signals in there. That is some strong signals that are frequency hopping around. It's a little bit easier to pull the signals out, see the pattern to it in the spectrogram mode. Now, this can also help you see weak emissions too. If you change your settings, your color settings a little bit, you can pull out weaker signals.
And what's the average noise for the LTE band?
The average noise, how they design it here in the United States, they try to design it at the base station to be about a minus 105 dBm. We've gotten debates with some of the cellular providers because, especially in urban environments where it's very noisy, to keep that minus 105 dBm noise floor. And sometimes that's difficult when you're in an urban setting with other transmitters, all those radiation sources such as LED signs, equipment inside buildings, computer equipment. It just increases the noise floor. And so call us and ask us to resolve interference issues when they find a source that really increases their noise floor above a minus 105 dBm. But sometimes it's not practical. In an urban setting, you may not be able to achieve a minus 105 dBm no matter what. So the best way to do that is to maybe sectorize your antennas a little bit better with filtering so that maybe you're not operating on the antenna, but sectorize your antennas, maybe use more than 3 sectors. Maybe you're trying to serve a certain area better. You can install a directional antenna so you're not getting the emissions from maybe that LED sign that's down the block. You're pointing the antenna away to better serve that area. Some of the tricks that they can use. All right, I'm going to stop sharing and let's.
Thank you, David. And everyone else, we do have a final program tomorrow, Friday, February 27th, on the overview of radio frequency assessments and on-site measurements. So please join us for that as well. Again, thank you, David, and thank you for everyone for sticking with us, and have a nice day.